Okay, question 2. We have 2 blocks. There's a mass m and a mass 3m, so this one's 3 times as large as this one. They're placed on a horizontal, frictionless surface. A light spring is attached to them, and the blocks are pushed together with the spring between them. Okay, so they're compressed. The cord initially holding the blocks together is then burned. After this, the blocks of mass 3m moves to the right at a speed of 2.65. Okay, so we can see the before and the after. And it's a multi-part one. It says, what is the velocity of the block with mass m? Okay, so let's start with that one. This would be a conservation of momentum. Okay, blocks are being held together by a spring. There's also going to be some energy that's going to occur in here, but then they're going to fly off and apart. So we see numerous examples of this with ice skaters or the archer and the bow, or things that start off not moving and in the end move, and we'll see that they move at opposite directions. So let's see here. I can have then that the change in momentum must be 0 because there's no outside forces being acted on here. So change in momentum is 0, which means mv final is the same as mv initial. Okay, and in the end we actually have both blocks that are moving, so I need to add in, make this mass 2, mass 1, v final 1. Okay, I'm going to have 2 blocks in the end. In the beginning I do have 2 blocks, but both of them have a velocity of 0, so I know that this part is equal to 0. If I start putting some stuff in, we can just call this mass 1, so just m. And the final velocity of mass m is what we're looking for. Mass 2 is just called 3m, and its final velocity was given, 2.65. And if all this is equal to 0, I can move this to the other side. I can minus it over. So let's take 3 times 2.65, and that gives us 7.95. So I'll have 7.95 m. It's negative because I've moved it to the other side, and this would be m vf, mass 1 vf. Now I've got an m on either side, so I can actually just kill the m's off, and it leaves with our final velocity, minus 7.95, and that's what the velocity is that we get here. Now it should make sense that this is larger, this block is smaller, so it'll move faster due to that spring. Okay, so Newton's third law coming into play. If m, okay, is 0.36 kilograms, what is the potential energy held in the spring before the cord is burned? Okay, so for that we need some potential energy of the spring. And we remember that US, the potential energy of a spring, is equal to 1/2 kx squared. But we have no information on K. We don't know how much the spring was compressed. There's a lot here that we don't quite know on the specifics of it. But it's okay, because all we're looking for is the potential energy. So all we need is this part of it. Okay, so all that we're going to do here is we'll look at the energy conservation. EF was equal to EI. Being it's an elastic collision here, we don't need to worry about anything. It's all elastic. Everything is conserved. There's no friction added. So we didn't look at EF is equal to EI. Well, what happens in the end? The spring is used and both blocks are moving. So in the end, we'll actually have 2 kinetic energies, 1/2 mv squared for the one block, right? And we'll have 1/2 3m v squared, because the other block is 3 times the mass for the second block, and both of them are moving. What caused them to move? Well, the energy came from somewhere, and it came from the spring, the only thing that could have been there. So that's actually our energy of the spring, is US, energy of the spring. So all we need to do is figure out this value. So if it tells you m here, so let's start plugging in some numbers. We'll have 1/2 0.36, and the velocity of m1 was found here. Now it's a negative, but it's going to get squared anyway. So I'll put it as 7.95 squared. And then we have to add in the second block. So I'm running out of page. I'll go down here. We have 1/2 3 times 0.36. And then the velocity of the 3m block. And the 3m block, it told us here, was 2.65. And that gets squared. All right, let's plug that into our calculator and make sure we get the same answer. And when we plug in, sure enough, we get 15.68, or we can round that up to 15.17. Okay. All right, so the last question is momentum conserved in the system or not? Well, momentum has to be conserved in this. There's no outside forces that are happening, especially because it says it's frictionless. Momentum in here has to be conserved. So yes, momentum is conserved. Why? You can state that it's frictionless. Frictionless. No outside force. No impulse. You could, I mean, the list could keep going on why this is a conserved system. You could say it's isolated. There's, you know, the energy is conserved. Hence, the momentum has to be conserved. Hence, you know, that's how that works. But yeah, anything in there is just fine. Come up with your own reasoning. Come up with your own words.